Okay. So let's work now on the ANI, I would say, definition, topic, challenges, and current solution. Can you hear me?
Yes.
Yeah.
Okay. So basically, can you see my screen? The ones showing the Miro whiteboard.
Yes.
Okay.
Yes.
So let's go for it. So clearly, the aim of the almost 1 hour we have in front of us is to first update our EMIRI key ANI priorities book roadmap that we issued on September 2019, where there is also a focus on hydrogen, but also to deliver some ANI topics at the end of this exercise. So let me share with you the whiteboard about production of clean hydrogen. And as I said before, there is in the column the challenges, what we want to identify, and the advanced material solution. And in line, you have each technology. So for the moment, we focus on alkaline, PEM, SOE, AEM, potentially alternative production route if you see some alternative production route. And we also included fossil-based hydrogen production with CC carbon capture. So I will dedicate 15 minutes, 20 minutes per whiteboard, so that we will be on time at the end of this exercise. So let's start with the alkaline electrolysis. I know, Jens, you were presenting a project on alkaline electrolysis. So I ask you here if you see specific challenge to alkaline electrolysis.
Yes, I think I talked about some. I mean, we need new materials for better performance.
So that's the solution. But what are the challenges you see? First, is durability, is cost, is
the challenges is the large footprint, the low rate capability. The old traditional electrolyzers, they can work for decades. They're just so large and bulky.
So how you will call it this challenge?
By carrying out projects like Next AC, where you develop new, better electrodes and better membranes.
Jens, I'm afraid that's the solution.
That's the solution.
The solution.
No, the solution is when you have done it, but the way to do it is to start the development. What do you want from me? No, I don't understand.
No, clearly, what's the roadblocks? Because having better electrode, better membrane, that's part of the solution. But what are could be durability?
Yeah, I saw it the other way. That the roadblock is that the present materials are not good enough. But okay, if we want to be there with an advanced system, then the main challenge is durability. That this harsh alkaline environment is really tough on most materials.
Okay. That's good. Do you see? I mean, okay. So this.
I can add one more thing. I think better understanding of what happens when gases are evolved from the electrodes and how bubbles are released. That is also be useful for designing better electrodes.
Okay, so the solution will be designing better electrodes. So this is in terms of architecture, but in terms of materials.
Yes, but to understand better how we get the gases out of the electrodes, how should they be in order to facilitate the transport processes that we need?
Okay, do you see something else on that? Because basically, you have challenges for alkaline, you have challenges which is durability, reliability, since both anodic and cathodic electrocatalysts exhibit deactivation after long-term operation, right?
Yeah, probably, especially if we make the new ones. We know that the old ones, which is basically nickel plates, blank nickel plates, plain, more or less, they last forever because there's nothing really that can go wrong. But they're not very effective.
Okay, so I'm asking for the other panelists if they saw something special. I mean, special, I would say, challenges related to alkaline electrolysis.
Karim, what about the inability to operate at high pressure, and also to operate at low loads? I'm not a specialist of alkaline, so disclaimer.
Yeah.
And also, I think the current density is usually quite slow in alkaline.
Yes, you're right.
Yes, that's what we talked about already with the low power density or current density. But you're right. The other issues here are also important. It's so desirable to run at high pressure, and some alkalines are working at high pressure today, 40, 35 bars. But we could, nice if we could go higher, but that will also require a different separator. And then the part load is also an issue for both alkaline and PEM, especially if you are operating it pressurized. So again, it's a membrane thing, the crossover.
Okay, and when you talk about, sorry, come back to this, to facilitate the transport processes, this morning we had the presentation from Beckhardt that work on that specific films. So basically, that's facilitate the transfer behind that. That's this thin film transport layer. Porous transport layer.
Yes.
Okay. Thank you. So I will move to the if there is no more contribution for the alkaline electrolysis, I will move to the PEM because I see some challenges here. Porous transport layer. Okay, so let's now talk about the PEM. So I see here 4 challenges. The first one is minimizing iridium and platinum loading while preserving performance. Yes. So any dedicated solution for that one? How do
Karim, I put this. So I think that there's a lot to be done on powder morphology and surface functionalization of powders.
Okay.
That's what I hear from the colleagues, but I'm also not a technology specialist, but that's the message I usually get from them.
Yeah, so it's making...
Marcel is in the call, I think he knows that very well.
You say, how do you say powder morphology?
And surface functionalization / coating.
Exactly, Fabrice, that's a good point.
Merci, Marcel.
Okay, that's good. So I just link it like this. Okay, then I see another challenge, which is ensuring sustainability of the electrocatalyst. Any input here for solutions for that one?
I put that, Karim, but I'm not so sure as whether it is really completely relevant. But it was just to highlight the fact that we need to embrace materials that are sustainable and safe by design. I know it's a keyword of the Commission. I don't have a material solution to that, but I just wanted to flag it.
Okay, I don't know, maybe Sabina, as you present something about recovering materials, do you have maybe a word here to say? About,
yes. So linked to this, I think that, for example, the eco design is an interesting, to check and to perform on this in order to yes, also connected for the manufacturing, but also to help the recycling. I think this.
Okay. Any after? So if I move to another challenge, please feel free to ask to the panelists to here feed the potential solutions. So I see there is other challenge which is reducing the production process cost of PEM. Yes, isoentropy alloy. Okay. Any input in terms of solution? I mean, materials, advanced material solution for reducing production costs?
No, I just put it as well because I think there's going to be more and more in the future convergence between the advanced materials and the production process agenda at the Commission. So it was also to flag that we also need to reduce the cost or increase the productivity of the processes by moving maybe more from batch to continuous or semi-continuous processes. But I don't think there's a lot of material solution to that.
Yeah.
But it was just to have it somewhere. Okay,
it's identified. There is actually, Philippe pointed out one of the main issue for PEM is the perfluorinated membrane. So for that one, what can be solution? I would say alternative materials, but do we know already some promising alternative materials?
That's for Bertrand.
If Bertrand is still here.
Yes, I already answered to this question. So I think the interesting alternative to perfluorinated material can be aromatics, that it already know to work in, I would say, harsh conditions regarding temperature, chemical, mechanical resistance. And I think it makes sense to investigate this area.
Okay, so if you allow me, I will move to the SOE. If there is no...
Just one thing I want to add. I had probably it's not fully the scope of the subject. I put anion exchange membrane electrolysis because it can be also seen as a real alternative to avoid using expensive catalyst. Because frankly speaking, if we have a look on the literature, we are talking about, I would say, decades of investigation to remove platinum and iridium for PEM without, I would say, clear success. Some important reduction, but no really, I would say, breakthrough. So why not seeking to this alternative anion exchange membrane technology in order to move to a nickel-based catalyst?
Okay, actually, Bertrand, for that one, we have dedicated a specific blocks on anion exchange membrane.
Okay.
So here we...
Sorry for... Oh, yeah, I missed it. My screen is too small.
Oh, I understand.
It's too small, huh?
I missed that too. I think some of the discussions on alkaline belongs to AM, but we can come to that.
Yeah, we can come to that.
Yeah. I didn't see that. Sorry.
Oh, no worries. So if I come now to solid oxide electrolysis, so we had here a nice presentation from Marie-Laure, and I think she felt a lot of those challenges. So first one was developing material with proof performance, reducing electronic leakage and electrolyte combined with stability, studying performance and degradation in relevant environments. Fair enough. Lack of multi-scale, multi-physics modeling tool to link material to cell and stack behavior. Okay. Demonstration scaling up for material. Okay. Operation at high current density and durability. So now let's move to the solutions. New electrode and electrode. So when you talk about new electrolyte and electrodes, do you have any insight here, more precise insight, Marie-Laure?
In terms of composition
or in terms of maybe nature of materials, and why not? I can add composition of materials and in terms of I mean the nature of the material too. Do you have any family of materials that could help here? I saw on the literature there is some perovskite.
Perovskite, they are old. This is a general family. So
yeah.
But I think it's also nice to try to look outside of the perovskite, but these are the most used. I think the difficulty here is that there are many good materials in terms of performance, but they are not so durable. So it's perhaps having a good compromise between performance and durability, which is the key.
But today there is no other path than using those perovskite family, right?
That sounds like, yeah, that would, at least at this stage, yes, those are the best so far.
Okay.
I would say maybe in terms of sustainability and thinking forward, maybe trying also to replace cobalt or reduce cobalt or critical raw material, for instance, that could be also sustainable by design. That could be also an approach there on a longer term. Okay,
but when you say get rid of the cobalt, is to replace it by what potentially?
That's a pity because the cobalt is the best.
It's not the best, only for hydrogen actually, for other application too.
So yeah, most of the perovskite, at least for the electrodes, they contain cobalt. So I don't have a good solution yet for you at this very moment, but
Okay.
Yeah.
What about the other? I mean, afterwards, somebody mentioned advanced method for surface functionalization. It's you, I guess, Maria.
Yes, that's me. Yeah. Another also opportunity to reduce, to enhance the catalytic activity of our oxides, which is also needed, is to use alternative ways of how to introduce or to stabilize the catalytic part. And for instance, exsolutions methods are very hot.
Also, when you advanced method deposition, I mean, liquid method deposition?
So that could be, yeah, it doesn't matter really. It could be liquid depositions, pre-coating, it could be what you want. So it's the advanced part is on utilizing the exsolution route.
Okay, and then it's more about modeling for electrochemistry flows. Okay.
Yeah.
So for me, there is one dedicated, I mean, specific to advanced material research, which is this one.
Yeah.
The other one is more about the process.
Yeah, manufacturing, yes.
Manufacturing, yeah. Okay, so I'm afraid we have to move to the anion exchange membrane.
Karim, maybe not only for solid oxide, but also for alkaline, a new development is the use of self-healing materials, like in batteries. So development of self-healing materials.
But this is something that you can add in every electrolysis.
Everywhere, in each column.
Yeah. Okay, I put it here and I did for the other one also. Okay. Sorry. Okay, thank you, Marcel, for this input. So let's now move to the AEM. So for this one, also durability, smooth release of gas from electrode. So I see a lot of challenge. One solution. Do you see specific solution to get rid of those challenges? Any input for the solutions? So I'm afraid we need to move to the other whiteboard. So so I will let you continue to those who are involved in the electrolysis business to feel what you think relevant, and please do not forget the solution part.
Maybe Karim, but I think that's also a cross-cutting approach, relying on artificial intelligence and this material acceleration platform approach that are pushed by Mission Innovation is probably something that could also part of the actions to be considered.
Okay.
Karim, maybe before we move to the next whiteboard, if people want to keep on modifying, maybe we can make sure that people do not edit a post that is not theirs, but add a new post if needed. right?
Yes, understood. So I just would like to let you know, to the audience, that we also have the alternative production and the other one with fossil-based production with carbon capture. So just to let you know that these whiteboards will not be closed by the end of the session. We will let the board living maybe 1 week, so that you can still give your inputs. So let's now, move to the other whiteboard. Just making the timer so that we are in time for fuel cells. So if we talk about the alkaline challenges, do you see some specific fuel cell alkaline challenges here? So if you need more time, I can move to the one which has already some challenges identified for PEMFC. But basically, yeah, I guess it's the same.
It's the same, actually. It's just we don't have the iridium issue.
Yeah, but do we know any specific challenges from fuel cell compared to electrolysis for this PEM technology?
I guess they are, but the broad challenges for me are these ones. But I can further look into it, huh? Unless Marcel already knows the differences.
If we take the ones that we used in the roadmap, that is one, reduce capex and opex by optimizing components, materials, and their manufacturing.
Okay,
that's
pretty much
OPEX.
this one, huh?
That's this one, right? Reduction production process costs.
Then secondly, improve performance and efficiency. At the same time, decreasing the weight of the components. So better performance, better efficiency at lower weight.
Okay, could we relate this one with minimizing plating loading while preserving performance?
Yeah. Yeah.
Of course, the challenges that Marcel is talking about is at the level of EMIRI and beyond. So I just put challenges which are the electrocatalysts related. So there must be challenges, of course, on the membranes.
Yeah, and on the bipolar plates, etc. That is a weight component. So improve the total performance and the total efficiency, decreasing the cost of the system. That's what we mentioned before.
Okay.
Then increase lifetime.
That's a very good point.
Cyclability.
Yeah.
And corrosion resistance. That is an issue in PEM fuel cells. Corrosion resistance, and all that to improve the durability of the system. And then finally, design for sustainability, circular design development.
Okay.
Like in the best for high, in fact. Enhancing recyclability, improving circular design, improving sustainability. That's what we had in the roadmap.
Okay. So now about the potential solution behind that.
We also still have the fluorinated membrane issue.
Yeah.
Okay, but I guess that's the same solution that we wrote for PEM electrolysis, right?
Pretty much. I think we can copy paste in the first iteration and then refine afterwards. Okay. I think.
Also, for the perfluorinated material, we can also think about, I would say, recyclability. frankly speaking, and I'm very interested about the last presentation of the project, but think that it is a thermoplastic material. So probably we can imagine the second life of this ionomer by, I would say, dissolving, reshaping, and I would say use in less demanding application. So I would say second life of material, it's also a way to improve life cycle assessment.
Because you think
yeah, I agree on this. Yeah.
This is something I haven't catch actually during the presentation. So you were able to recycle thermoplastics, right, Sabina?
Yeah, we will recover ionomer.
Okay, yeah.
Yes.
But that's a little bit more the concept of direct recycling, which is still at a very low TRL for the moment. At Umicore, we recycle fuel cells PEM, and we actually use the process we have for recovery of platinum from automotive catalysts. And our process captures all the fluorine, of course, at the level of an element, which we can mineralize, but at least the fluorine content is contained. Maybe direct recycling is an option, but it's we're not talking about TRL here, but it's much lower TRL, so it's a long-term track, I think. But it was exploring.
Yeah. Okay. Do you see something else on PEM, FC?
Not from my side.
Okay. So let's move to SOFC. So I know, Marinor, if you are here, I know you are more specialized on electrolysis, but in your configuration, your technology is able to make also to be in fuel cell mode.
For SOFC, I think one of the interests is to couple it with ammonia fuel cell. So here, stability and durability of the ammonia-based electrode is a challenge.
So why you want why you want to work with ammonia fuel cell?
Why do I want to have ammonia and fuel cell?
Yeah, because that's the solution actually. It's answer which challenge?
No, ammonia. Okay. Ammonia fuel cell is a technology solution, yes, maybe. But if we want to operate the fuel cell with ammonia, then we need to have to check on the durability of the electrode. So improve the electrode or challenging, yeah.
Okay.
Durability of the ammonia electrode. Yeah, here I would say high production cost. It's also an issue for whether SOFC or PCFC, so reducing the cost.
Okay. Basically, do you have also the same solution for SOFC and SOEC?
In terms of production?
Yeah, for production costs, are you going to use I don't know, low-cost materials, or what do you see behind production costs?
The way so SOFC are mostly planar technology, and it's multiple coating and casting coating and reduction processes. So overall, it's an expensive. It's quite expensive. They also use crystalline oxide. Our production technology with the PCEC is a bit different. So it's a bit hard to compare. But we know that the cost of SOFC is still high right now, and we need to decrease it. So maybe utilizing advanced technology like 3D printing, that's something to consider. And automation, bringing more automation in the process to decrease labor cost is also something to consider.
But 3D printing could apply for also for planar technology too.
Yeah, of course. So that is.
So it's an answer by process.
Yeah, that could be one solution. Also integrating automation in the processing line is also another answer.
Okay.
Marie-Laure, I have a question for you.
Yeah.
For the, I'm clearly not an expert in this field of SOFC, but for me, it looks a lot of analogy regarding what organic electronics is doing to, I would say, apply more solution process fabrication in order to decrease carbon footprint and cost.
Yes.
And I'm just wondering, does it make sense, I would say, to try to pick some nice or good ideas in the field of organic electronics that can serve this field?
Of course. So here is, I'm not an expert on organic electronics, so but definitely I think it's having some cross idea. Yeah, it's definitely, this is something where we could learn a lot, I think, or have some good solution.
Okay, but here the issue, I think, for processes that have been developed for organic electronic is the temperature of the process. And here for such fuel cell, okay, when you think about the operation temperature, I'm afraid the processes could not be can be a nice.
Karin, I'm Jose Luis speaking. I know that working in roll-to-roll process as well for doing membranes and so on and components and just to have the electrode over. So that is roll-to-roll is coming from the polymer electronic. Let's put it. So, but they're trying to apply this also for the fuel cells and also to have cathodes at all the layers. They try to do this as well because it's a continuous. You automatize and you do the process faster as well.
Yeah, that's what I meant by automation. So
yes,
that's an example. Yes. So reducing the labor work and having more faster process, bulk process. That's a key.
Okay, so basically the answer is the process, but again here you don't see
any production cost. In terms of durability, there are very good results published by a number of very good research group, and it is pretty good. So now it's a matter of cost and also scaling up.
Okay, and you don't see any breakthrough in terms of materials.
Well, I don't see that this is I don't think this is the limiting challenges. So I think now they have done so good there that of course you can always improve, and like I said, also remove cobalt in this type of material or nickel if you want, but I don't think this is a critically limiting factor here.
Okay, I just put it here. Okay, so if you allow me, I will move to the AMFC. Somebody, identify two challenges for such a technology: carbonization and membrane stability. I don't know who has put those challenges, but do you have any solution to put in front of those two challenges?
I put them there.
Okay.
And I know it's claimed by some people that the carbonization problem is not so big with membranes, AMs. I'm not sure that it's correct. I don't know. But it's certainly a problem with a normal liquid alkaline electrolyte. So they normally operated on pure oxygen or scrubbed air where you remove the carbon dioxide. The thing is, the carbon dioxide reacts with the potassium hydroxide and precipitates and fill the pores. So that's a fundamental problem. That's one of the things that has held the alkaline fuel cells back. In the electrolyzer, it's not a problem because gases are going out and not going in. But in the fuel cell, this is a problem. But the alkaline fuel cell has some very nice features, very good oxygen kinetics. It's very, and it doesn't rely on platinum metal. So it's very attractive in some ways, but it has this carbonization problem.
Okay, and here from by now there is no solution foreseen for this carbonization issue.
Well, you can clean the air, but it's just so much air you have to blow through the cell. So to remove the carbon dioxide from all that air, that's of course challenging and tedious. But if it's used together, we say you want to store energy by electrolysis, you store the hydrogen. If you store the oxygen as well, then you don't have this problem. But then you need to store two gases instead of one.
Okay, so one of the solutions could be to store oxygen.
Store oxygen. Yes, yeah.
Thank you. And what about the membrane stability?
Yeah, that's the same as with the with the electrolyzer. I think good membranes have to be developed. So that's ongoing, and many groups are working on that.
Okay. Then, okay, is there any other fuel cell technology that we probably missed here? I take it as a no. So then let's move to the last whiteboard, which is about storage distribution. Okay, so you see here the compressed technology. Yeah, of course, one of the issues is hydrogen enrichment. So protective metal coating to the person that put the solution. Is there any coating already identified? Okay, well, so, or do you see any other challenge for compressed hydrogen solution?
Costs, perhaps. They're very nice tanks, but they are also expensive.
Mm.
I'm not sure what to do with that, but I suppose we can write cost everywhere in these schemes.
Yeah,
that's always an issue.
Yeah, the cost is due to the carbon fiber vessel.
Yes, and long time in a machine, probably.
Yeah, and it seems to be the winning technology for cars.
Oh yes,
unless
no doubt.
Wrong, unless I'm wrong, but do we see here any breakthrough or new technology that could overcome those carbon fiber vessels? Yeah, vessel recyclability. Because here I don't know. I let you the floor maybe to comment. I know the liner is also an issue here.
Yeah, and I would say everyone is thinking about the Type 5 vessel for hydrogen in order to have a multifunctional material that can be, I would say, the structural part of the tank and also the hydrogen barrier materials in order to have a linerless solution. But what I see today, Type 5 reservoir is still a fuzzy concept for me.
This is Bertrand.
Yes.
I think right now, yeah. When you say about this biodiffusion of hydrogen, do people are thinking about making liner that are the biodiffusion, or make two different coatings?
I don't know if you know the difference between Type 4 and Type 5 reservoir, but the idea is in Type 5 you have linerless solution. Mm-hmm. So that means the structural composite part also do the job as a hydrogen barrier. And that can be a way to, I would say, avoid this liner presence and this liner issue that usually suffer from, I would say, compression, decompression. I would say the normal cycling life of this kind of reservoir. But also we can imagine to have, I would say, better adhesion regarding the liner and the structural part of the reservoir in order to avoid this liner collapsing issue.
Okay, so then, Bertrand, do you know any solution avoiding this liner issue today?
As I say, the solution is to remove it totally. So that means the structural material have also to manage the barrier to hydrogen. And this is what it is described in the literature as the type 5 reservoir. So it is one possible solution, but there is probably other, as you mentioned, a functional coating that can, I would say, replace the liner, or also investigating other polymers. If I remember well today, we are talking about polyethylene. I would say it's more, quite basic thermoplastic material for the liner, or polyamide. Maybe there is some room of improvement regarding the liner chemistry.
And today, do you know what is the current TRL of such a solution?
I don't know exactly the TRL. The best what I know is the example what Forestia is doing in Belfort. They have, I would say, quite available production tool to provide reservoir to more or less all the actors in this field for, I would say, in Europe area. I'm not clear what is really the TRL level for the type 4 reservoir today. I'm not an expert to go in this detail.
Okay, thank you very much, Bertrand. Any input with the problem of, with the challenge of thermal stability? Somebody raised.
Yeah, I put it there. Today, what's done is that the hydrogen is pre-cooled before the container is filled, and that, of course, requires energy. It's down to -40 degrees typically, and then it ends up at 85 when you fill it. Yeah, I don't know, heat exchangers or something, but that's perhaps not so easy. We need to have more feed through, so probably have to live with that.
Yes, or probably we have to think about how to tune thermal conductivity property of the tank in order to, I would say, spread this thermal hotspot due to the pressure gap during the rushing operation. Because with metallic vessel, it is not an issue because due to the high thermal conductivity of the tank, which is not the case with composite material.
Yes. So I just raise it as a question, but I understand that there is no solution foreseen at the moment.
It's not on the shelf solution, I guess.
Not on the shelf. Okay, but that's an issue. So I just here I just link it like this. That's linked. Okay. So if there is no more comments on compressed technology, I move to liquid cryogenic storage. Is there any challenges here? I guess that's what BMW said before this morning, all the boil-off issues. Do you see any other issue or challenges? So Jens, I see that you start to write something, high energy for liquefaction. Yeah. I don't know if we had today a community representing this part of the value chain, or at least this technology. Yeah. So that maybe I skip it and I move to hydrides, if you allow me. Okay, that's here. So first challenge here, identify each hydrides bring compromise between cyclability, weight, volume, or cost. Where does it make sense to use hydrides? So potentially against about or not convinced about hydride solution and heat management on board vehicles. Okay, solution foreseen here, hybridizing hydride system, utility scale system with different approaches on hydrogen charge and discharge. But if we focus on materials or advanced material solution, and Any input of potential breakthrough here or on hydrides?
I think that depends. I wrote that one. Where does it make sense to use it? I mean, we've always dreamt of using them in vehicles, and I don't think that is practical. They are very heavy, that's one thing, but all the heat management is really, I think, the real showstopper here. So it could be some smaller applications where it might make sense. I'm not sure where exactly, but I think for the large high energy on like vehicles and above, I don't think there's a bright future for the hydrides, I'm afraid.
Okay.
That's the fundamental properties, that you have this heat balance. You need to apply enormous amounts of heat, remove enormous amounts of heat when you charge them. When we fill a pressure tank at a gas station, it's between 3 and 5 minutes. And imagine that a large portion I sometimes tell my students, say, imagine you're filling your car with gasoline, and 10 to 15% of the gasoline burns inside the tank while you're fueling it. That amount of heat you have to remove in a few minutes.
Yes, but that challenge can be addressed, I guess, by material solution or by system management, heat management systems.
Materials is difficult because that's thermodynamics. If you want certain pressure temperature relationship, you're stuck with the heat. But of course, a very efficient heat exchanger could, in principle, solve this. But I don't think it's practical.
Yeah,
and the weight percent of hydrogen is higher in a pressure tank than in any hydride tank. Any hydrogen tank that works. I mean, if you sodium allanate is the most advanced, that it's actually more or less reversible. You cannot beat a high pressure tank.
Okay. I don't see any enthusiasm things
Sorry.
about hydride. So if somebody wants to make to promote hydrides, that's the moment. Otherwise, I move to the other technologies. Okay. So 1, 2. Okay, let's talk. Sorry.
I would promote an hydride with much higher weight percent of hydrogen included than the present 10% or whatever. So very high loading of hydrogen, novel materials with higher loading of hydrogen.
And where would you use it?
Yeah, not in automotive. That's not evident.
Okay. So now, sorry. Okay, so let's move now to the last technologies, which is LOHC. I mean, inorganic can be not relevant, but let's focus on liquid organic hydrogen carrier. So Vincent, you made a nice presentation about that. Any other challenges foreseen here? I remember you talk about the energy needed for dehydrogenation for LOHC technology, but do we see a solution in front of that?
And the need in PGM.
The need of PGM, yeah. Yeah, it's written here, yeah. We'll try.
Okay.
It's written here, but so as you're working on that, what could be your solution here?
Okay, it seems that biosourced molecule need catalyst, which not PGM.
Have you already seen some, I don't know, in the literature, some biosourced molecule?
Yes, there are some examples. The fact is that the hydrogen loading is a little bit lower, but the enthalpy of dehydrogenation is also lower.
Okay.
So it's a compromise.
Okay. Any other comment here?
I think there's a different here if we think of what goes on with fuel cells on a vehicle. It has to be quite fast. This process, if it's not meant for vehicles but for transporting hydrogen between countries and so on, we can perhaps live with a poor catalyst and a slow process, because it doesn't have to happen in real time, so to speak. It could happen. I mean, you ship the substance somewhere and load it there, and then they can take a long time liberating the hydrogen. Perhaps that will be allowed, or they can take a long time charging it with hydrogen. So you can do with the less efficient catalyst, and then do without the noble metals.
Okay. So that's part of the solution, but at the end, it depends also on catalyst.
Yeah, I'm not so familiar with the catalyst used here, but we were told today that it is platinum typically used, and it's difficult to replace that. So if we can give in a little on the reaction rate, then we could perhaps do with a poor catalyst.
Yeah, right.
Karim, Umicore, we are investing with Anglo American on LOHC technology.
Mm-hmm.
That's a lower TRL as is this. I mean, it's a low TRL today, but I'm not too much into the details. So I will ask my colleague to have a look at the Miro and to contribute to the input, but after tonight.
Okay.
If it's okay for you.
Yeah, it's fine. I mean, as I said before, we are going to let this Miro whiteboards available for a few days, so that we will still get some input from the hydrogen community. Okay, so Vincent, you identify some specific materials, I mean, family also in your presentation, but I can't remember which ones.
Family of what?
Of family of LOHC, I mean, couple of LOHC.
Oh, the one I have indicated are just state-of-the-art material.
Okay.
And the need of associated PGM catalyst material. Yes, we have identified some molecule, but I don't want to integrate their name today.
Okay, but basically, okay, so I understood. So basically, the problem with LOHC is the energy demand for the dehydrogenation and the PGM catalyst, right? There is no more challenges.
They are the two mains.
Okay.
Cost perhaps. I don't know how expensive the carrier is.
It depends. In fact, if it's toluene methyl cyclohexane, it's cheap. If it's dibenzyl toluene, it's expensive. So it depends on the molecules.
My other concern also for that kind of molecules, I guess, is the environmental friendliness of such a molecule.
Yeah, it could be toxicity, yes.
Okay. Any other? Yes.
Yes, I have a question. Why? Because they are also chemical carriers for hydrogen, like ammonia, other ones. So they are not considered there.
Look, I can here others, and we can add some challenges here if you want.
Because I was reading inorganics, okay, this could be the solvents, because then you come to a different situation, because you have to, okay, you have the hydrogen, you have to have the catalyst to develop to synthesize the ammonia is the chain we have in the project, where you have developments in the catalyst for synthesis of ammonia, because the transportation is cheaper than transporting hydrogen, because the volume is much higher, the amount of hydrogen you can transport. And then you have the catalyst for the synthesis, and if you want to use as a hydrogen, you have the catalyst for for the composition of the ammonia as well.
Yes, correct. Another
And the sorbent materials also, sorbents can be also to store, they can be used also to store the ammonia is one, or you can use it to improve the synthesis, because you are also removing a product from the reaction. So you promote the reaction, no, in the equilibrium you move when you, it's like chemical looping with the CO2 and so this, but you do with the ammonia, you know.
Okay, so but for catalyst, so that's
because there are different things I can put here. This only translating is you have ammonia, you have to deal with several things.
Mm-hmm. Okay.
And we also work in increasing the amount of ammonia you can store in the sorbent as well. That could be linked with an inorganic, because will be an inorganic carrier, in fact, because you have to store, but with absorption with B, and then you can also store this as of the ammonia.
So, but here okay. So I write it down here. The challenges about catalyst ammonia synthesis, but also catalyst for ammonia decomposition. So, but do you have already some solution there, or it's still?
Yeah, they are developing materials. I will feel later. I have this information, okay, but I would like to cross check these are public or not. That is the point also.
Okay.
Yeah, but I see they're referring to amides and things like this, and also catalysts without platinum group metals as well, for in both cases as well. And then the sorbent, I can feel this information later on.
Okay, so with that, I will close our working session right now, and we will end up this meeting. So, by the way, I want to thank all of you for your active participation, and also special thanks to the project. I mean, the EU project coordinator, which, I mean, you've made some wonderful presentation, and without you, those sessions would not have been possible. So, thank you. Let's move to the other point of the agenda. And please, as I said before, this MyRose will be still available for a couple of days. So we will send to you the link so that you can still working on that. So let's move to the last point of the agenda, which is the wrap up and conclusion of the day. So I have to say that one of the keywords of this day was circularity. This morning there was a lot of industrial, but also this afternoon project coordinator emphasis on recyclability, circularity. We saw also a lot of challenges in every value chain of the hydrogen economy, from the electrode, from the membrane, but also I really enjoyed the presentation from Becca when they were explaining the issues on porous transport layer, and also see some specific high temperature PEM technologies. So that's my my key takeaways, and now let's finish our work on identifying R&I needs. So you will hear about us quickly after this session. So thank you again. So I give you the floor, Philippe, to conclude. Maybe Fabrice, you want to say words also?
I just wanted to say thank you to everyone, and this is just the first step, but it was a very interesting day.